Hello everyone. Today I'm going to talk about polynomial functions. It is at the section 2.2 in our textbook. So let's start with the definition. How about this? Let me start with some examples. And actually I claim that you guys have seen a lot of polynomial functions before. We just haven't called them polynomial function yet. So example, say you have this f of x equal to, say, 2x plus 3. Very familiar, right? This actually we usually call it the linear function. Or graphically, if you graph this, you're going to have a line, right? Slope is 2, y-intercept is 3. Linear function. Or this one we just learned it recently. F of x equal to 3x squared minus 4x plus 1, and we call it the quadratic function. Okay? You guys see the format, the type of this function? In general, we have a bunch of terms, right? A number times x, and a plus, and a number without x. And this one, what? A number with x squared, and then plus minus, a number with x, and a number. Okay? And we're gonna develop this type of function a little bit more. Instead of just having x, just x and x squared. What if we have x to the third power, x to the fourth power? Those type of function. Say this: f of x equal to negative 2x cubed minus 4x squared plus 5x minus 1, and I claim this one is also another polynomial function. All right, and so forth and so on. You can have degree 4, degree 3. Oh, by the way, degree means the highest exponent right here. So all of those. This is a polynomial of degree 1. The second one is a polynomial of degree 2. And this one right here is a polynomial function of degree 3. And usually when people first study this is called linear function. It's called quadratic function. And this one right here, by the way, is called cubic function. And then degree 4 is quartic function, so forth and so on. But in general, from now on, we're gonna call them the polynomial function. So in general, before giving you guys a formal definition, a polynomial function is what? A function that looks like those forms right here. A number, later on we're going to call them the coefficients, okay? Number times x raised to some exponent plus another number times x raised to some exponent, so forth and so on, all the way to the end. Okay? So let me put out the definition. Number 1, definition. A polynomial function is a function of the form f of x equal to, now that I don't know how many terms I may have, x to the 4th, x to the 5th, x to the 6th, x to the 7th in general. So let me just write it x to the n. Okay? And then next term going to be x to the n minus 1. And then we're going to have some number in front. So there'll be a lot of numbers. So let me denote the number by letter A and index n. So this is number an. So we say with x to the n. So the next term is going to be a n minus 1, x to the n minus 1. And then of course what? A n minus 2, x to the n minus 2, so forth and so on. Keep going. So a2 x squared, a1 x, and then a0. Let's box this first before I talk more. So if you have function of this type, a number times x to some power plus another number times x to some power, so forth and so on, all the way to the end, then we're going to call it the polynomial functions. Okay, so in here, a0, a1, a2, all the way to an, we call them the coefficients. Right, notice it's numbers, think of it that way. Okay, and of course an, you guys know this before, this is the leading coefficient. Okay, and we have one condition for an. An needs to be non-zero. Of course, if it's 0, then you don't have this term right here. It's not the leading term anymore. It's going to be an minus 1. It's the leading term. All right, that's the definition. Now, I was going to talk about the properties of this, but let me try to talk about the definition a little bit more. So we have number n right here. It's called the degree of the polynomial. This is an R, okay? So the degree 1 polynomial, degree 2 polynomial, degree 3 polynomial, so far. We have a very special one that's degree 0 polynomial. Means what? You don't have any x terms in here, only the constant at the end. Right? For example, f of x equal to 5. This is a polynomial function. All right, but actually we used to people don't call it polynomial. It's a constant function, y equal to 5. And graphically, what is it? Horizontal line at y equal to 5. Okay? This is a polynomial of degree 0. Degree 0. Very special, but it's pretty trivial and easy to take care of. Just horizontal line, straight line. Okay? Even more special than this, we have something like f of x equal to 0. Now what? It's violated the condition right here. Claim what the limit is going to be non-zero, right? This one's everything is 0. This is even more special. This is a polynomial as well, all right? Still a polynomial function. Still horizontal line as a graph. But a little bit more special. This is the x-axis. Okay, y equal to 0. And what is the degree of that thing? Depends on the book to define it. Some book call it define. Some book define the degree. This one is degree undefined, or degree negative infinity, or degree even -1. You read some books that I've seen one book two that call this polynomial of degree -1. It's okay. But anyway, just a special case, and I think it's simple, easy for you guys to take care. And all I will try to emphasize what those are trivial, but actually they are also the polynomial function. Okay. Now let me move on to the second item. First one, the definition. Second topic, I'll be talking about some basic properties of polynomial functions. All right. Number 2, properties. The very first property that I'm gonna bring to you guys is about the graphs. Of course, it's impossible for me to give you guys the precise graph yet, okay? Unless you have a calculator or you move on to the next level, calculus 1, when we know about derivative, and at least we have a better understanding of the graph. But for now, I can give you a rough approximation of the graph of polynomial functions. And I claim that the graph of a polynomial function mainly depends on 2 things: its degree and leading coefficient. Okay, so let me demonstrate the work by drawing a table. Okay, the degree could be even or odd, and the leading coefficient could be positive or negative. So if you have a polynomial function with even degree and positive leading coefficient, then I claim that in general the graph somehow going to look like this. Okay? Could be wiggling a little in the middle, but eventually at the ending behavior on both sides, left and right, the graph tend to be going up. Okay? So the leading coefficient, positive leading coefficient will tell you what? The graph tend to go up. Okay? Even means what? Both ending gonna be in the same direction. And similarly, what if you got even degree but negative leading coefficient, and the graph gonna be upside down? Alright, same shape, just flip it backward. So negative leading coefficient will tell you what? The graph tend to go downward. Okay? Even degree, both ending will be in the same direction. Let's move on in here. Odd degree, but positive leading coefficient. And I claim the graph you guys are going to see looks like this. So what? Odd degree tell you endings, the 2 ending behavior are going to be on the opposite direction. Okay? And positive leading coefficient will tell you the graph tend to go up from left to right, go up. Okay? Of course, odd and negative is going to be backwards, so go down. All right, so let me show you guys some typical examples to convince you that actually it works. Take a look at the easiest one. Say linear function, f of x equal to 2x minus 3. Okay? Of course, we don't talk about trivial cases in here with polynomial of degree 0, horizontal line, or degree -1. Still horizontal line y equals 0. Okay, that's trivial. Talk about polynomial of degree 1 or higher. Let's apply the table right here. This is a polynomial of degree 1. 1 is odd. Leading coefficient is 2. And you know that this is a line. Slope positives go up, right? That case right here. How about quadratic function? F of x equal to 3x squared minus 4x plus 1. Degree 2, even. Leading coefficient 3, positive. And everyone knows it. This is a parabola. Open upward. Onto this case right here. Okay. The higher degree, then the higher chances you're going to have for the middle behavior right here, go up and down, wiggling a little. Okay, this smaller degree, the graph looks simpler. Degree 3, how about this? F of x, say, equal to negative 2x cubed plus 7. I claim that the graph is going to look like this. Okay, this case right here. Odd degree, the graph looks like up and this way and that way. Negative leading coefficient, graph tends to go down. Oh, it's going to be like this. Okay. Degree 4, f of x equal to x to the 4th, minus x squared. Right? Oh, by the way, this one we're missing what? The x cubed, right? The x term and the number, right? That's fine. That's fine. You got the leading coefficient is non-zero, which is 1 in this case. So in what you want to write all them out explicitly, it's going to be this: 1x to the 4 plus 0x cubed minus 1x squared plus 0x plus 0. So the coefficients are 1, 0, negative 1, 0, 0. But this is easier. Okay? And it's still polynomial. And I claim the graph of this one, degree 4, even, positive leading coefficient. Okay? The graph has to be like this. Like that. Okay? This case right here. All right. So actually, I did not show you how to get a precise graph of any polynomial. I'm just showing you that by looking at two basic things, the degree and the leading coefficient of a polynomial, at least you can roughly have some idea of how the graph of those functions is going to look like, right? And that gives you a hint to learn something more later on. Of course, I'm going to show you in a couple of minutes. This is the very first property that we learned today, the graph of polynomial. Next, I'm going to talk about another very important property of polynomial. Actually, we'll talk about 3 things at once because those 3 things are related to each other. Property number 2, I'll be talking about zeros, talking about linear factors, and x-intercept. Alright, so how are they related to each other? Let's start with an example. Say f of x, let's make a very simple, easy one. F of x is equal to, how about this? X squared minus 4x plus 3. As you see, this is a polynomial of degree 2 with leading coefficient 1. But in short, it calls a parabola, quadratic function. Graph is a parabola upward. Like this one right here. Okay. Let's talk about something else in here. Now, question, can we factor this out? Now, of course, I chose easy, a number of simple functions, so it's factorable. Of course, f of x is equal to, you factor out, you have x minus 1 and x minus 3. Right. So far, so good. Question: what if we try to plug 1, x equal to 1, into the function? See what we got. I claim those two functions right here is the same, okay? It's just the general form and then it's just factor out. We got two factors, okay? Oh, by the way, linear factors. We have a polynomial degree 2 right here. When we factor out, we're gonna get two linear factors. It's x minus 1 and x minus 3. Those are two linear factors, all right? What if we plug 1 in? So f of 1. You can plug in either the original one or the factor form of the polynomial function. See what you got. 1 squared minus 4 times 1 plus 3, or 1 minus 1 times 1 minus 3, and likely in both cases is going to give you equal to 0. So what are we seeing in here? When we plug 1 in, we get 0 out. Input x equal to 1, output y equal to 0. Okay. And with that, we are saying that x equal to 1 is the 0 of the polynomial. X equal to 1 is a 0 of the polynomial of f of x. Is the 0 means that when you plug that value in, when we plug that input in, we get the 0 out. And some people, I think it's quite a number of people, feel not very comfortable with the 0 right here. Choose another word. It's you can call it what I think solution or root. You can say what x equal to 1 is the root of the polynomial, x equal to 1 is the solution for the polynomial. Those are the values that when you plug in, you receive back 0. Okay? And you see what? If a function, polynomial has x equal to 1, that's a 0, and we're going to see that we have a linear factor that associated that 0, which is x minus 1. You see why? 1 minus 1 is equal to 0. Okay? And this is, by the way, this notation means equivalent. Right? This saying is equivalent to saying what? X minus 1 is a linear factor. Factor of f of x. You see why? You plug in x equal to 1 and what? X minus 1 equal to 0. Okay? And what about the intercept? You see? 0 is equivalent to linear factor. What about the x-intercept? You see what? X equal to 0. I'm sorry, x equal to 1, y is equal to 0. So this saying is equivalent to what? At 1 comma 0 is an x-intercept. So you guys see that those three things that we are learning right here, the zeros, the linear factors, and the x-intercept, they are equivalent to each other. In other words, if you know 0 of polynomial, you'll notice it has a linear factor, you'll notice it has an x-intercept graphically. Okay? And similarly, this graph, this function, does have another 0, which is x equal to 3. You see it right here. It's a 0 for the polynomial. Equivalently, x minus 3 will be a linear factor, and 3 comma 1, I'm sorry, 3 comma 0 will be the x-intercept. Okay? Question: what is it good for? Why do we have to know that? What does it help me to learn about polynomial? Say you have function f of x. Okay? You didn't know everything about it. You don't even know the function yet, but you know some about this. You know that, say you plug in x equal to 4. You got f of 4 equal to 0. That's all you know. And according to what we learned right here, f of 4 equal to 0 means that x equal to 4 is a 0. It's a 0 of f of x. Right? Because 4 in, 0 out. Are we good? And according to what we learned right here, we know a 0 means that we know a linear factor. We know that x minus 4 will be a linear factor of f of x. So that tells me that even though I know very little about the function, I didn't know everything about that function f of x, but at least is a factor right here. At least I will know that f of x can be expressed as x minus 4 times something, because linear factor is a factor. So what? X of x 4 times, I don't know what it is, for g of x. Okay? Want to make sure that this is clear to you guys, because it's the same thing of saying this. Take a look at this thing. Say I got our number, 14,562. Okay? And I see right away this is going to be an even number because it ends with a 2. Okay? What does it tell me about even number? Divisible by 2. And that means that it's going to be equal to 2 times something. Right? Right? Same thing in here. So have a factor of x minus 4. So f of x is going to be equal to x minus 4 times something. Of course, the next question I guess you may ask is, what? How in the world I'm going to find that something right here? For this problem, simply divide both sides by 2, because you know this number, you know this. Okay? So, if you know the function f of x, and you know it has a factor of x minus 4, how do you find the function g of x? Same idea, you take f of x divided by x minus 4, you'll be able to find the function g of x. Okay? And in order to do that, you guys recall something that we learned before. If not, then I'll come back to this and I'll talk about this in the the next section. I think it's about called what? Synthetic division or long division. You're gonna be able to figure out a g of x, but that's not for now. Just try to talk about zeros, linear factors, and x-intercept. So you guys got all three. Okay, there is one more thing, and still a distraction, okay, in this topic right here. Let me make an asterisk. Talk about this called multiplicity. Does tell you how many times a zero or a linear factor is repeated. Let me give you an example. Say f of x equal 3 times x minus 1 squared times x plus 2 times x plus 4 raised to the 3rd power. Okay, so in this example, I actually factor everything out for you. Okay, you see what? X minus 1 squared, x plus 2, and then x plus 4, 1 cube, right? So we can actually write this way: x minus 1 times x minus 1, x plus 2, then x plus 4, x plus 4, another x plus 4. All right. Question. You know the degree of that thing? This is a polynomial of degree 6. See why? We have 1, 2, 3, 4, 5, 6 linear factors total, right? So if you multiply them all out, the highest degree, the highest exponent is x to the 6. So 6 could be the degree, and of course 3 right here is the leading coefficient, right? So I guess the graph somehow like this. Could be wiggling a little more in the middle, I don't know, but it's going to be pointing upward, okay? And both spreads at the same side. Okay, well, let's go back to what we learned in this item right here. Zeros. You guys see all the zeros of this polynomial? They got 3 zeros actually. X equal to 1 is 0, x equal to -2 as another 0, and then x equal to -4 as the 3rd 0. Okay? Now, how many zeros of x equal to 1 did you have in here? 2, right? Because you have 2 linear factors of x minus 1 and another x minus 1. So we say that x equals to 1 is 0 with multiplicity 2. X plus 2, just 1, so multiplicity 1. X equal to -4, 3 of those, so multiplicity 3. Okay? And you can find the degree of polynomial by add all the multiplicity up. The degree is 6, we got 2 plus 1 plus 3 is equal to 6. Okay? Now the next question is, what is so good about multiplicity? And I can tell you that multiplicity, let's give you some more information about the graph of the polynomial. Right? So we have 2 types of multiplicity. Even. Let me some E. even multiplicity or odd multiplicity. So obviously x equal to 1 is even multiplicity, multiplicity 2. X equal to -2 is odd multiplicity 1. X equal to -4 is an odd multiplicity 3. Okay? And if you have a zeros with multiplicity, means what you're gonna have. Well, we learned before we have x in the set, right? So in here we have 3x in the set. 1, comma 0, x in the set. -2, comma 0, that's another x in the set. And then what? -4, comma 0, that's a third x in the set. And I claim that the multiplicity will tell you different type of x in the set. Okay. So for even multiplicity, just assume this is the x-axis. Okay. The graph gonna getting closer to the x-axis, and then it's gonna bounce back. Of course, the other side too could be this way. Okay. And we call it what? Tangents, or informally, we call it what? It's touching the x-axis. Okay? We say what? The graph is tangent to the x-axis. Tangent. Touching. Wow. Okay. For even multiplicity, you have tangent. Just touch and then bounces back. So what? The entire graph is going to be on the same side on that local region. Okay. For R, it's not going to be that way. When it's go down, it hit the x-axis, it's going to go through. Of course, the other way around as well. When we go up, we go through. It's crossing the x-axis. Okay. So with this example right here, at x equal to 1, the graph will be touching, will be tangent to the x-axis. Okay. And x equal to -4 and x equal to -2, the graph will be crossing the x-axis. Okay. It hit the x-axis, go through. Okay. That is about multiplicity of the zeros or of the linear factor. Okay, let me move on to another item, another property of polynomial. Number 3, turning points. Right. So let me just randomly draw a graph of polynomial. You trace along the graph, you see what happened. The graph go down and go up, and then go down and go up, go down and go up, right? So the turning points. At the point of the graph change the directions. Okay? So this is a turning point. The graph go down, hit the bottom, go up, and hit the bottom, go down, hit the bottom, go up, hit the bottom, hit the top, go down, hit the bottom, and go up. So those are 1, 2, 3, 4, 5 turning points. Okay, the turning point is just a point in the graph change direction. That's what we call this. But those points for now. But I claim that later on when you guys get to I think cut 1, those actually what the local minimum, local maximum, local minimum. Go down, hit the bottom, go up. So locally, this is the lowest point. Local minimum, local max. Okay. For polynomial of degree n, you will have at most n minus 1 turning point. I say at most, okay? So if you have a polynomial of degree 5, you will have at most 4 turning points. You have a polynomial of degree 10, you have at most 9 turning points. And the number of turning points in a polynomial will be different by a multiple of 2. What I mean is this. Say you have a polynomial of degree 5, then you may have either 4 turning points, or 2 turning points, or no turning points. You have a polynomial of degree